So here we go. So here is that. It's literally the exact same equation that I showed you before. But what we did was I multiplied this negative 2 mu e over h bar squared back through, okay, and collected like terms for the potential energy. And that's what the equation now looks like, okay? So we've got our negative h bar squared, 2 mu, second derivative in radius, and that's perfectly our kinetic energy operator. And now we get what's called an effective potential energy operator, which is this whole chunk in the parentheses, okay? And then, of course, that's times u of r, and then now all of that equals E times u of r. So what we've done here, we've eliminated the angular component, and really, I shouldn't even say that. We haven't eliminated the angular component. We've just reduced the angular component to its eigenvalue, which is that negative L times L plus 1, okay? So the angular wave function is not in here anymore, okay? Even so, I'll still remind you that my psi of r theta phi equals, let's see, that's going to equal, you know, the radial component times the YL ML theta phi component. And I know that my u of r just equals r times r of r. So I have a Schrödinger equation, right? This is my Schrödinger equation. There's my eigenvalue and my radial wave function that I need to solve for. And once I solve for that radial wave function, once I find a solution for u of r, then I can multiply it by r, right, to get, or excuse me, I would divide it by r, rather. And then once I get that solution, I plug it back in, and I'll have my total psi. So that's where we're going with this, okay? As it turns out, though, this Schrödinger equation can only be solved for various boundary condition cases, which is actually true of all of our Schrödinger equations. However, these solutions become a lot more condition specific. So there's three conditions we're going to look at. When L is equal to 0 or when L is non-equal to 0, when the electron is very close to the nucleus, or when the electron is very far from the nucleus, okay? And it's all about the angular momentum. And that's why we have these condition-specific cases, okay? So for example, I'll remind you that, so if we go to the next slide here, when L is equal to 0, the electron has no angular momentum. So let's not quite go into this yet. Let's just focus on that. So when L is equal to 0, there's no JZ component. There's no angular momentum on the z-axis, okay? And so now if we were to look at this effective potential energy, right, looking at these two terms right here, this is entirely, so here's the L equals 0, that's entirely what I'll call Coulombic. So in other words, we notice as the particle gets closer to the nucleus, right, as the radius decreases, the potential energy is really falling off. And I know it's going to negative values, but that's because when we developed that Coulomb's law in the first place, right, Coulomb's law is a negative potential when you have an attractive force, okay? So that's another condition that we're going to create is for all E's less than 0 for any bound state. So because of this Coulomb potential, right, because this Coulomb potential says the more attractive a force is, the more negative the potential gets, we have to also create this additional boundary condition that says for any bound state, the energy is less than 0 by definition, okay? So when L is not equal to 0, there is angular momentum on the z-axis, okay? And we'll see that there's competition now between the particle getting attracted to the nucleus and it getting flung away from the nucleus because it has angular momentum, right? So let's explore both of those in more detail, okay? So when L is equal to 0, and specifically when R is very close to the nucleus, so when this says R is almost 0, that means very close to the nucleus. So the electron has no angular momentum, and the force of the proton on the electron is purely Coulombic and attractive, okay? So that means that there's several chunks of this equation that we can eliminate, all right? So for one, why does it all equal 0? So I want you to compare this equation right here. We're going to compare this to the full equation that I showed you before, okay? Well, we know when L is equal to 0, right, this whole chunk goes away. So we don't have that to deal with anymore, all right? And now what we have left, and excuse me, also, why does this approximately equal 0? Well, it's approximately equal to 0 because we know that U of R equals R times R. And if this R is nearly equal to 0, then that makes the whole function nearly equal to 0. So that's where this whole side of the equation eliminates. Okay. And we don't eliminate it over here because, again, we're taking an operation on it. We're doing a derivative on it. Okay. And so now you notice what we have left when we go through that and pushing our constants through again, right? So then we get the ddr squared of u of r minus, and then now look at this, 2z over ar. So I collected all those constants for the Bohr radius, and there it is. Okay. So now for this condition, our Schrödinger equation becomes very easy to solve. So this entire big nasty Schrödinger equation just reduces to this very simple form, and the approximate solution of this wave function is given by this polynomial. Okay? I'm not going to go through the ansatz method on this equation. We're just going to rely on this approximate solution for now. Okay? So it's a polynomial. So when L is equal to 0 and when R is very close, we can describe our wave function with this polynomial. Okay, let's look at a different